So welcome everybody to today's session on energy and machine learning and how we should be thinking about these two coming ever closer together. So I'll just give a quick sort of overview of the day. So we're going to start off with my very quick intro to what we mean by machine learning in this context, so everyone's on the same page. And then we'll have a quick introduction from each of our four panelists telling us who they are, what they're doing, and how they are using machine learning to revolutionize something to do with energy. We have a very broad spectrum of applications there. And then we'll move into a couple of prepared questions just to get things rolling, but then quickly move on to audience questions. So if you have ideas for our panel, things you'd like their thoughts on, or specific questions on things they mentioned, put those in the chat. You can send those directly to me and I'll start kind of collating those, or you can just put them out there for everybody and I'll skim through and pick them. I might then call on you to read out your question if you just want to write a question. Otherwise, I can paraphrase for you as the discussion kind of flows. And then we'll move on to, at the end, a couple of student presentations to highlight some of the work coming out of UVic on these topics. So to start us off, why do we want to talk about this today? So machine learning has kind of grown, I guess, exponentially in the last few years out of things being done in Silicon Valley, all of these kind of revolutions from Google and Facebook and so on, that these companies are really driving this area forwards, as obviously are lots of academics as well, including lots in Canada. So this area is coming to everything. Everything is getting swallowed by this beast of machine learning. And what do we really mean by that? So to me, it's a way of using data. Some people describe it as just statistics with bells on, but I think it could be more than that. I don't want to particularly get into the technicalities of how we define it, although maybe the panelists will have comments on that later. But fundamentally, it's ways of using our computational methods, much as we've done for many years in a kind of a physics-based sense, embedding these things we know about the world. Machine learning takes a different approach and tries to derive that meaning from the data itself. And so two very broad categories would be whether you're starting from labeled data, you know something about your data already, and you want to train something to be able to classify something, for example, based on those labels, or that kind of thing. Or you could start with unlabeled data and have your machine learning algorithm in itself try and learn from scratch what sense is there in this data. And I'm sure you can think of lots of possible applications across our domain of energy. So we'll talk today about buildings, about power systems, about transport, lots of different domains where this could be applied. The areas you see it kind of out there in the world, I'm always very scathing, and I say that all our best and brightest graduates are stolen by Silicon Valley with their six-figure salaries, and they have them like tagging cat videos on Twitter or whatever. Like the applications of these things are in those areas perhaps not so useful, but then we can take those developments and bring them back and apply them to areas that might actually do some good and save some energy and save the planet, etc. So whereas traditionally this data might consist of images or videos or web searches, we can also apply this to time series or to geospatial data or performance data of systems that we've simulated using some other program, or data that we're gathering from our energy systems. This has been a big change in buildings, and that we're now getting so much data. IoT, kind of Internet of Things devices, are spitting out so much data about our buildings, about the world around us. And we need better ways of starting to understand that as researchers or as industry practitioners to make some sense of this. So that's my incredibly brief overview of how this revolution has perhaps started, where we're getting these algorithms from. Many of us use codes developed by computer scientists for other purposes, but are applying them in this domain of energy, where we're trying to have these algorithms almost do our jobs for us, but like certainly find some sense in this data for us. I think that's enough intro from me as to the very broad overview. I obviously can't do this huge field very much justice in 5 minutes, but to keep us on schedule, because we do have a packed timeline today, I'm going to get each of the panelists to introduce themselves in 5 minutes, say what they're doing, where they're working, what cool stuff they're working on to revolutionize, machine learning. So to start us off, should we start with Elena?
All right, thank you. Hello, everybody. My name is Elena Popovic. I am a computer scientist at heart and by training. I got my PhD from George Mason University in the States, and I've been working in industry after that for what has now been about 15 years or so. I started my career in a scientific business consulting company. I was there for about a decade, and I essentially applied a wide variety of computational techniques, including machine learning, but also other things like optimization, network science, modeling and simulation, data analysis, to a really wide spectrum of domains. But then a number of years ago, I made a sort of a deliberate shift to the clean tech sector, and more specifically clean energy. And yeah, my first foot in the door in that space has been here in Vancouver with a company called Nurio. They've a couple of years ago been acquired by a larger US company called Generac. And they made a sensor, an in-home sensor that was measuring electricity consumption at the beginning, with the goal of just making people aware of how much energy they use. But from that, they've broadened to also measuring generation from solar panels, and also operation of home batteries. And so while I was there, I worked on algorithms for optimizing the operation of home batteries to try and reduce the peak demand, which is a big deal because it has an impact on the grid. It's also a big deal for the consumers because they may have to pay more for consuming energy at particular times. And also, in order to try to help improve these algorithms for operating the batteries, I worked on actual machine learning in the more traditional sense of the word, for time series forecasting. So to try and predict the consumption of a home in the upcoming hours or days, and the same for generation from the solar panels, and try to feed these forecasts into the battery operation algorithm to try to improve its operation. And then I made the switch to the other side of the puzzle, which is the grid side of things. So now I am head of data science and CTO for a company also here in Vancouver called Osense. And so they make software for utilities, like BC Hydro is one of our clients, as well as a number of other utilities out there. And on the grid side of things, it's actually the network science part of computer science that tends to be a bit more important, but there are still opportunities for ML to help in the space. One of them is, for instance, for estimation of missing values in time series. So what Osense is trying to do is to build a platform to bring together the structure of the grid, all the geographical distribution and connectivity together with the time series. And the data is always messy, so there's room for these computational techniques to help clean it up and bring it together. And on the side, I also do some consulting for the Foresight Clean Tech Accelerator. So there I work with the technical people at these startups in the clean tech space to try and guide them on how to bring their technologies to market, and what computational techniques they might need, how to build their teams, and so on. So maybe I will stop there. Not sure if I've used my 5 minutes, but.
That was perfectly timed. Thank you, Elena. So let's go next to Sahand.
Yeah, thanks, Rolf. So my name is Sahand Behboodi. I graduated 4 years ago from the University of Victoria, Zurich. I joined Benbody, which is a software company based in Vancouver and Denver. They hired me because of my simulation and optimization skills. I started as a systems engineer doing data analysis, and then like big data, and prototyping model to hand them over to the software engineers to make a production, basically software. I worked on a few machine learning models that we had at the time, basically developing models, in Jupyter notebooks, and then just like write, epic documents, hand them over to developers. But they found them maybe complex. So they basically asked me, why don't you move from operations team to the software team and actually code this yourself and help us like do the work? So I moved after 2 years to the software team. I'm a mechanical engineer by heart, but became a software engineer. And so I work with them. My title is cloud software engineer, and basically help them put together different models for like machine learning, for load forecasting, etc. And the other work I do is like I'm in charge of, our databases and like basically collecting, monitoring like data, and like we have an ocean of data and like what we can use this data for. I work with with operation team a lot because actually I moved from that team, and we have this software to control distributed energy sources, like like from AC units to electric cars, the small remote generators, and use things I learned from my time with UVic and like from operation team, transferring the knowledge to the software engineers. It's actually like interesting position to be there, understanding both languages from mechanical engineering to software, translating that. And yes, that's my story.
Great, thanks, Sahand. We'll see how much this conversation gets into the bridge between the people doing the stuff and the people building the software to do the stuff, because in my head, those are very close to how we're talking about machine learning versus other types of simulation. That's great. Okay, let's go to Yi.
Okay, so I will share my screen. Can you see that?
Yes, that's good.
Yes.
Okay, that's great. So I'm Wang from Etienne Zurich. I'm now a postdoctor at the Power System Lab. And my research interest is mainly on smart data analytics. So I got my PhD degree from Tsinghua University in 2019, and my research interests mainly include data analytics for smart energy systems, cyber physical power and energy systems, and multi-energy system integration. So maybe you will know that we are on the way to the digitalization of the power systems, and in this way, various data will be connected by widely installed sensors. So my research is mainly on nice on this kind of data. So a massive number of data can be connected, but this kind of data should be transformed into knowledge or into information, so that we can provide deeper insight into the past and better in understanding of the future, and also practical advices on the possible decisions for the digitalized and low carbon power and energy systems. And my research mainly focuses on the demand side. This figure shows a typical demand side active distribution grid. You will see there are different participants. For example, the consumer, buildings, industrial consumer, and also household. And we have also load aggregator, distribution system operator, and electricity retailers. They have their own business models based on this kind of smart data. So my research, you can find that it contains 3 parts. The first one, data management. Sometimes we have so many smart data, so we need to compress the data set so that the efficiency of data analysis and data transmission can be boosted. The other one is the anomaly detection. If you have a lot of data, there are so many anomaly data, you need to transform it or clean this kind of data sets. The other one, data generation. Sometimes the data is very we need to develop a deep learning neural network or something like that. It should depend on a very large data set. Sometimes the data is limited, so sometimes we need to generate a lot of data. And based on that, I try to model the consumption behavior from data-driven perspective. I think the consumer behavior can be defined as follows. The consumer, him or her, can use appliances so that a lot of load profiles can be generated and their own utility function can be maximized. So my research wants to make a bridge between each pair of these components. For example, for the consumer and load profile, I want to identify the social demographical information of the consumers from the load profiles. I also want to design the prices, personalized prices to maximize the utility of the consumer or also the retailer according to the profile. And I can also recognize the patterns of the from a massive number of load profiles, so that the appliances can be identified. We also have two extensions. The first one is the spatial extension from each individual consumer for a large number of consumers, because if the size of the consumer, if the number of consumers increase, their consumption behavior will change. And the other one is the temporary extension from current consumer to future consumers. So sometimes we need to do load forecasting. So each item means I have done some works about that. So, so the main goal of the research is my research is to have a better understanding of the consumers, so that we can promote friendly interaction between the consumer and the energy grids. So you can find more works in one of my book is Smart Metadata Analytics, and the president of the IEEES, Professor Saifur Rahman, also wrote a foreword for this book. He said this book is worth reading, and one will see how much insight can be gained from the smart metadata alone. So this is a picture that I have developed software. It's about load forecasting and also for consumer behavior analysis in Guangdong province. Now this software have been used. It is now being used in all the 21 cities in this province, and they can they can boost their forecasting performance by making full use of more fine-grained smart metadata, so that they can make a better decision if they want to decide how much electricity to purchase and to sell from the generator or to the consumers. So it will they get more benefit from this software. So this is just simple of the industrial application. So that's all my presentation. Okay.
Wonderful, thank you, Yi. Great deep dive into some of your different areas of research that we will touch on later. Okay, and then our fourth panelist is Martine Tran.
Hi, everyone. First off, thank you very much, Ralph, for the invitation. Very pleased to be here. So my name is Martine Tran. I'm an assistant professor in the School of Community and Regional Planning at UBC. And I run a lab called the Urban Predictive Analytics Lab. I guess somewhat of an ambitious title, but the logo that we have is the logistic map. So some of you that have studied complex systems may know that the level of predictability becomes highly intractable very quickly. And the logistic map is a great example of remaining humble and demonstrating a bit of humility in terms of our ability to predict. And I think that mantra goes forward also with a lot of the potential, but also the limitations of various computational methods, including machine learning. And so I hope we can get into some of that discussion today. I'll try to bring a bit of a different perspective in terms of much of my work is focused on mobility and at scale, at the neighborhood, at the city scale, and indeed trying to compare cities to other cities. There are some intersections, though, of course, with facilities and buildings. I did my PhD in the UK, and my PhD was actually on electric vehicles on the demand side of things. And as a postdoc, that took me into collaborating quite closely with building energy modelers, particularly in the context of the discussion at the time and even today. And there's still lots of outstanding questions the ability for electric vehicles to act as distributed energy sources, the so-called vehicle-to-grid configurations, or even vehicle-to-housing configurations. So that was a good opportunity to engage with building energy modelers at the time. And I guess there are some analogies between building energy modelers and my own background coming from transport systems modeling. So when I entered the field, much of the, I would say, a lot of the questions were fairly well tackled in terms of the potential on the technology side, in terms of alternative fueled vehicle technologies, the potential carbon reduction performance of those technologies over time. So we had a pretty good understanding of that. And I think the same thing fairly holds with building energy modeling systems on the supply side of things. I think through the well-developed physics-based models, we have a pretty good understanding of the carbon reduction potential of that. The weaker point, I guess, in transport systems modeling, and I would probably say also in building energy modeling, is on the demand side, the behavior. And so that's where I focused much of my research. And that research has continued to this day, but looking a little bit more broadly now. And so some of the work that my lab is conducting, there's various threads, but I guess I would say there's 3 buckets, and one bucket is really trying to understand broad mobility patterns, and not just necessarily the mode of which by which people travel, but really asking the question where people are going and why, and trying to understand those broader mobility patterns. So that intersects with facilities management. And so I think there's some potential crossover questions there in terms of trying to manage energy and carbon potential emissions reduction from a facilities management perspective at the broader scale. And I think to this day, even you don't have transport people talking to building people, and I'm not too sure why. It doesn't matter where you emit carbon, it all adds up. And I think there's also, when I was still to this day actually in the field, there is some kind of implicit assumption that people wake up in the morning and they schedule all of their activities, depending on if they're inside a building or whether they're outside a building. And we know that that's not true. We tend to organize our time in terms of time budgets and the destinations at which we are trying to reach. And so I think there's a lot of potential to think about demand patterns in a much broader perspective. That is, how activities inside a building also add up to activities outside a building, and the entire signature in terms of the energy signature of a person throughout the day and throughout a spatial context. So I think there's a lot of potential for discussion from that perspective, a much more integrated look at demand patterns throughout a city, and trying to understand the energy consumption from that perspective. So in the context of specifically machine learning and the various approaches, I guess my own background comes from various different computational methods. From the climate mitigation field, the original field from which I come from the so-called integrated assessment models, which is bringing together physics-based models with econometric models to try to understand different aspects of the economy. And so in that sense, we always struggled for data, actually, and now there is just a lot more data, and that data is being generated either through mobile applications or the so-called Internet of Things on infrastructure. So I do think there is a lot of potential in this context with all of this new data being generated now. And just to give you a bit of an example of some recent work that we're doing, we are trying to improve our understanding of behavior in the city. One aspect of it is trying to collect a bunch of social media data and trying to use that to supplement our understanding of demographic data, that is taking conventional census-based data that's collected, which is highly aggregated. And I think that's where one of the potential real benefits of different machine learning applications is to bring higher resolution to data sets. And in this context, what we're doing is we're using both computer vision techniques to try to, in a very specific application, we're estimating age using social media, using computer vision techniques to better understand age profiles of demographics throughout the city. We're also applying another technique called sentiment analysis, and this is leveraging natural language processing to try to understand, which is basically text analysis in this context. So we're trying to understand the sentiment and the behavior of travelers. What is their experience? And specifically, we've just finished up some work on trying to understand travelers dependent on transit throughout the pandemic and what their experience is. And there is some potential there for trajectory analysis also, but the data gets a little bit more scarce in that perspective. So all of this is trying to bring greater resolution to trying to understand behavior. And the hope there is to try to improve behavioral interventions in terms of carbon reduction policies. So that is, I think there's a lot of potential for that, but I would highlight, and I hope we get into this discussion a bit more, that this whole field is rife with challenges and a lot of, I think well-intended challenges in the context of data privacy, data security, and really the need for policy and regulation to catch up with the technological progress that's taking place right now. So I'll leave it at that, and I hope we can get into some of these points for discussion later on.
Brilliant, thank you, Martino. I wrote down a few of those points to cover later, and I'm sure we'll get more specific questions about those. So that's our panel. I think we have 4 people covering a diverse basis of application areas, from grids to demand management in buildings to transport and broader kind of economics models. And they've each spoken about sort of quite a different approach to this, from a very software-driven sort of making things and bits of code that are out there in the world to academic and sort of how we're developing the underpinnings of those in our research. Some commonalities I noted. I think every panelist used the phrase "understanding patterns" at some point. This is, I guess, the crux of machine learning: is what's going on out there in this system, in this world that we're trying to capture. And I think every panelist also used the word behavior at some point in their explanation of what they're trying to capture. What are the people doing? What is that intransient piece that our physics models perhaps aren't that good at, that the data is telling us, because the data really is that ground truth of what the people out there are doing, whether it's where they're driving to work or where they're charging their batteries or where they're turning their devices on and off. So I think that gives us a great basis to start with our first prepared question that I asked our panelists to think about. So this question is, what machine learning methods and application areas have the most potential for upheaval? So how are these algorithms going to change what we're doing? And perhaps we could tackle the methods part of that first, to dig into some of these technicalities, because maybe we are still talking in very broad strokes about machine learning as a whole. We could take this opportunity to dive into what particular sort of tools from our toolkit are we seeing as most practical and useful here. So who would like to start off on methods that they see as most promising? Sahand.
I can go first. Yeah. So when we started for the pattern recognition, like to understand the load shape and the behavior of their consumers, in my company, people wanted to use simpler models, like traditional machine learning models like ARIMA, which is like combination of like autoregressive and moving average, like all things. that you could develop it using, I don't know, some Excel spreadsheets, which was a good starting point. But we very soon like realized that's not the way to go. We wanted to use, more like deep learning, approaches, because why not? We have the computational resources. We were using like cloud infrastructure, so cheap, available. So why not? Why not like using AWS to basically train our model and like do a better forecasting work with that? So end up trying all the available like methods for neural networks, like recurrent neural networks, the long short-term memory, gated recurrent unit, like different like models, and going there, understanding that each method has its own advantages and disadvantages, and we don't need just to use one single model for everything. For example, in our case, we have this project. We wanted to find out what the peak load is in a utility, and so we could run a very expensive model. The model can take, I don't know, like 1 hour, to train the data, have the model, and just like forecast. But we had other projects that you wanted to predict the load on a particular water heater, and within the utility we had like 1,000, I don't know, 1,000 of them. We wouldn't want to develop a model for each water heater and run it. It would take like days to finish that. So just want to throw this out, like there is like no one good model, that there is like nothing that you can use for everything. There is no magic model. You should try everything. You should see your resources. You should see like how fast your model should be, how accurate it should be, and then based on that, basically implement it.
Maybe I'll follow up on that. Yeah, so we actually have a name for that in computer science. It's called the no free lunch theorem, and it applies to both optimization and supervised machine learning. So that, yeah, I just want to reinforce that point. And to kind of broaden it as well, maybe I think where I see the upheaval coming is in bringing multiple methods together. Rather than like, let's get this particular method a little bit better. I think we need to bring together the time series forecasting that is just data driven with the kind of forecasting that is more model driven, that's from the simulations, from the behavior of the people or of societies, and then together also with optimization and control algorithms. Because I think the difficulty right now, especially from a grid's point of view, is it's like it was said, they don't necessarily talk to the transportation people. They don't necessarily talk to the building people. They don't have visibility into how they're going to be impacted by electrification of vehicles, or electrification or buildings, installing various kind of distributed energy resources for like batteries and solar panels and stuff like that. So I think that the things need to come together. The simulation side kind of trying to give the grid a view on what might be coming, the grid trying to figure out how am I going to deal with these things coming, and put in place various kinds of control, because DERs, as great as they are for emissions, they come with challenges. The grid was built to be like a one-way flow, whereas what's happening right now is that the flow is becoming more and more bidirectional, and that is difficult for utilities to manage. So I think for me, the upheaval is in approaches that try to connect the methods, is what I would say.
So I would like to follow up. I want to point out 2 points. The first one is explainable machine learning. For example, sometimes deep learning model have better performance. For example, it can have very high accuracy for stability prediction, something like that. But it's very hard for the engineers to apply this kind of method because it's hard to explain the result. Yes, so sometimes we need to explain which factor contributes more to the result, which factor, how different factors influence with each other for and contribute to the final result. So this is, I think this is the main challenge for, or how to say, if the machine learning techniques cannot be explained well, maybe it's very hard to be explained, to be applied in power industry, because we put more emphasis on the stability and the reliability. It's high risk to use unexplainable machine learning. The other one is the privacy preserving machine learning, because sometimes we run our machine learning model on a data set. We assume that we have access to all these kinds of data, but sometimes, for example, smart meter data, this kind of smart meter data may be owned by different consumers or by different retailers. The system operator have no access to this kind of data. So how to develop privacy preserving machine learning techniques for that? So this is the 2 point. This is the second point. For example, federated learning or something or some other techniques can solve this problem. So the other one is also from privacy preserving. So sometimes I want to share my data with system operator or something like that, but you should pay some money to me, yes. So how to value the data? So the data valuation is also very important in the future digitalized power systems, so that we can incentivize more consumers or more participants to show their data, to train a better model, so that the system can be operated in a safe and efficient status. So this is my comment.
Yeah, Ralph, maybe I can jump in here too, because I would strongly endorse the last two sets of comments there. Yeah, from, as I mentioned, some of the work that we're doing right now is bringing together different methods to try to tackle a single problem, and I think there's a lot of opportunity for that. So this is the broader area of data fusion techniques. So bringing different strands of data together. And as I mentioned, when we're looking at trying to understand demand patterns, mobility demand patterns through time and space within a city, we're using both computer vision and natural language processing to try to understand that demand profile. I think there's other opportunities there to bring in trajectory analysis, things like this. And so there's a lot of opportunity there, but I also strongly agree with the comment from Yi, which is about model interpretability. And that's a fundamental debate that's happening right now. And I think there's interesting questions for and against. And I can, so the for argument in terms of, for model interpretability is many of us come from, much more conventional methods, physics-based models of that, and we control the parameters, the input parameters, and see what the output is, and then we can understand what is going on with the model, why we are getting a certain result. When you're dealing with millions of parameters and the amount of data that's being used right now, this is not tractable. Now, the argument there is, if it works, then we don't need to deal with it. But in very narrow applications and more benign applications, and maybe not so benign, like recommender systems on Netflix and things like that, I think that's fine if it seems to work. But I think quickly, particularly in the context of climate change, and what we are getting into is a domain where these tools will potentially help inform policy. And then this becomes a challenge, I think, when it starts to get into broader societal questions, the inability to interpret the models that may be underpinning policy decisions becomes quite problematic, I think. Now, there are advanced techniques, Bayesian analysis and these types of things, which I'm not an expert in at all. But it is certainly a field that I think is worth exploring, and new techniques to try to understand the interpretability of these different models. And alongside that, we will still always need the other types of physics-based models, I think, to support those types of applications. And I would also strongly agree with the idea around data privacy and data regulation. And specifically, I work with municipalities. One of the challenges that I see coming from that perspective is right now cities are being approached all of the time by startups and industry and that to deploy their technologies and improve their algorithms. And I think this is of benefit. I mean, there's reasons for this. Funding has dropped from municipal purses, and so they're more reliant on partnerships with industry, and they want to partner with industry. But I've seen it firsthand, the case where startups or industries are deploying their technologies, but they're keeping the data. But the data and the algorithms are being tested and deployed on publicly funded infrastructure assets, and the city isn't getting any upside of that. So I think as the discussion moves forward, there needs to be much stronger thinking between public-private partnerships in this context. I mean, we most certainly do not want to stifle innovation, but at the same time, municipalities have a certain responsibility to answer to citizens and also respond to processes such as citizen engagement and things like this. And we've heard all of the stories around, the Sidewalk Labs example and how all of the hangups with that because of the lack of citizen engagement. And that was, probably quite a missed opportunity. Some of that technology would have been fantastic, but they didn't go through the proper processes. And there was a lack of policy framework to govern data sharing, which was really the crux of the problem there. So I think these are some of the challenges that we'll face alongside the deployment of machine learning techniques.
Great, thank you for your comments, everybody. If there's no further quick remarks responding to anyone's points on methods, I will just take a very brief moment to go back a stage and perhaps fill in some minor gaps in the explanations of some of the stuff that was being talked about there, building on my initial interpretation. So I think we covered lots of different methods there. Sahand brought up recurrent neural networks and long short-term memory, LSTM networks, as a class of kind of time series forecasting machine learning approaches. Another piece of terminology is this talking about deep learning, which in the context of these neural networks just means add more and more layers and go as deep as you can. And so then when these methods are trained, this leads to this problem of the lack of transparency, that you can't tell why the model says what it says. It's giving you some answer, but you can't necessarily tell why, and then therefore have this degree of explainability. So that leads then to this problem of this lack of interpretability or transparency. If a municipality, in Martino's example, says to a citizen, this is why algorithm says X, they have this problem of explainability. And there's also methods being explored to try and address those points. Okay, so that maybe moves us on to part two of that question, talking about applications. So we could interpret this in terms of particular domains, and I think everybody has their kind of their particular area, but maybe think about an area where within that field you see the most potential of applying machine learning. Or Martino's point leads us directly to sort of who is applying this. Perhaps is this municipalities, is this startup companies more broadly who would be doing the applying. So who would like to start off on that?
I'm happy to jump in, Ralph. Yeah, so alongside all of the, I think the cautions, there is certainly a lot of excitement, and so I'm really excited also from a research perspective. It's early days for myself and my lab, but one of the things that we are excited about is using satellite imagery and applying computer vision techniques to it to try to understand the relationship between different demographics at the city scale and access to infrastructure services. So we have done some testing around this, and It's the results are too early to really suggest anything, but we are having fun with it. And I think here this is using a combination of both bottom-up techniques and top-down techniques in terms of scale. So using satellite imagery at scale to look at cities in terms of their morphological properties, but then doing deep dives into right down to the neighborhood level where we do have fairly good census data, combining that with the types of other data sets that I had mentioned, and really trying to understand the correlations of certain households in terms of their socioeconomic status and their level of access to different infrastructure services. So we have done some work around this from the bottom-up approach, looking at key amenities within cities. So that is hospitals and clinics and schools, and trying to understand household access to those things, and then doing some forecasting and seeing how those accessibility patterns change over time. One of the things that I'm really excited about is then bringing in the carbon question to that, to try to understand what are the potential co-impacts or co-benefits of accessibility to these different services, and then trying to understand. So when we lay it all out in a spatial configuration, we can also compute, for example, the travel time to these different services, and then we can make assumptions about the different travel modes by which different households get to these services. So therefore, we can then compute the energy consumption and therefore the carbon emissions. So I think one of the things that I'm quite excited about is trying to understand both the equity question in terms of accessibility to services as a function of households, combined with what the energy consumption patterns are related to those different travel patterns. And so I think there's a lot of opportunity to look at it from a much higher level using satellite imagery. Also, there's been some really interesting work using Google Street View right down at the neighborhood level to try to understand the types of infrastructure and the states of infrastructure at the neighborhood level that is in proximity to these different households. So again, going back to this, bringing multiple methods together to try to tackle a single problem, I think is quite exciting.
I can take a stab at the part of the question that was what would be needed to help ML techniques have more impact and assist in the energy space. And I'll focus on a particular slice of the ML space, which is the time series forecasting, the load forecasting that has been mentioned so much. And I think in my view of what's happening in this space is that the models to do the approaches, the techniques to do this kind of forecasting, there's a wide variety of them, and they yield pretty good performance to the extent that this stuff is forecastable, because humans are kind of inherently, unpredictable. But what is difficult currently with the existing tool sets is keeping the learning going and maintaining performance over time and adapting. So there's training a model once on a historic data set, testing it on a holdout set can get great performance. You deploy it out in the real world, and then say something like COVID happens, and all of a sudden everybody works from home, and all of your load forecasts for the commercial spaces will change, and all the ones for the residential spaces will change, and your models won't work well anymore. So there need to be some tool sets for monitoring performance and trying to detect when something is no longer working, and then mechanisms for trying to then figure out how to retrain and to bring back the performance. And I feel like the tool set to make this work happen is not quite out there yet, both from maybe scientific standpoint of like what criteria should we use for deciding that performance has dropped, what kind of relearning should we do, how much more, maybe we should use more recent data, or like when should we retrain and how should we retrain. There's some scientific work to be done on that side, but also on the just like the platforms and the software to help manage something like that is not quite there yet. There are the Amazons and the Microsofts that are working on these, as far as I'm aware, to incorporate them in their machine learning platform offerings. But you know, like I said in a workshop like maybe a month ago, and it was like, yeah, we're working on it, we don't have it yet. So I think that will be good there, because doing forecasting at a really fine grain level, at like the house level or even the appliance level, is a lot more difficult than doing it at the region or you know, aggregated level. And so those needs to be, and there'll be lots of them also, right? Like there'll be millions of consumers. You gotta, if you're gonna train on a per consumer basis, you have to maintain millions of models, you have to monitor them, and then you have to retrain them. And that is a lot of, is non-trivial, let's say. So yeah, both scientific methods and actual software tool sets to support that, I think, would be great.
So I totally agree with Elena that the method should be updated online so that more situation can be modeled in the machine learning model. For example, we are now organizing a node forecasting competition considering the impact of COVID-19. There are several teams that participate in the competition. The teams using LST model or some other very complex deep learning model have very worse performance because of COVID-19. The trained model cannot fit the new situation, but traditional model, for example, the similar days-based method, time series-based decomposition method or something like that, have better performance. So it's very interesting. So my idea is that if we can provide so many open data sets, for example, the data set for electrical vehicle charging and discharging, and also the load profile before and after COVID-19 or something like that, it will be much beneficial for both academic and the people from academic and industrial to train the model so that the model can have, can be adapted into different situations. The other one is also for open, it's open code. Because, for example, in the computer science, so many people make their codes open, yes. So everyone have access to this kind of code, but it's not the case in power engineering, where it seems that the people in power engineering not so willing to share code with each other. So it will delay. For example, when I do my research, I have to reproduce the result by myself. So it's time consuming. It's hard to, maybe it's to make the progress too slower or something like that. So this is the second point. The other one is that sometimes we need to combine integrate the deep machine learning with the power and systems. Sometimes we just want to use the off-the-shelf machine learning tactics, for example, deep learning networks, and also for other fancy machine learning tactics. But this kind of application should be based on a deep understanding of the end systems. For example, how the forecasting accuracy will influence the operational cost of the systems. Is it possible to integrate this kind of cost into the machine learning model instead of mean square error or something like that? For another example, if we want to do power flow analysis, is it possible to embed this kind of knowledge of Newton Raphson method or something like that into machine learning model, so that we have so this kind of integration will improve or will help the machine learning application in a wide areas, in a wide area. Yes, it's just my personal opinion.
Just remembered something related to this. So when I was learning machine learning, like beginning working as a data scientist, I guess like maybe 90% of my time, I was just cleaning data, and I was trying to reproduce what other people have done. And so I had the data set, it was public, even the model was there, but I was not getting the same result because I have used, I was using different methods for data cleaning from them, like how you deal with the noise, how you do, I don't know, maybe feature selection. And so one thing that I wanted to bring up here was like the data integrity and like what you do with data. That's also a very important part, like to consider before actually comparing different, like, forecasting models for like resolution of data you get. Or like it happens a lot that we get like time series data and we actually don't know this date time, is it like UTC or it is, is like the local time. So that may cause like issues. Yeah.
Very good points there, everybody. Did anyone want to respond to anyone else's comments there or build upon those?
Yeah, I will do a quick follow-up. I know we're a little bit behind, but I think it also gets at a question that was asked in the chat, which is the trade-off between accuracy and speed, simplicity of the model versus performance. And what Dr. Wang just said, this notion of can we incorporate in the machine learning the true metric of performance, if you will, which is what are you going to do with that prediction? You're going to feed it into some other system and there's going to be an impact there and performance will be measured differently there. So I think that relates to the question in the chat as well about how do you go about it? Well, you have to think about what are you going to use the prediction for. And I have some lived experience of this when I was trying to use load forecasting to improve battery operation algorithms. And the true performance was how much better was the battery doing. And it turned out that, the level of accuracy that you could get out of the forecasting had a really, you needed something really high at times in order to actually be able to improve the battery operation. Otherwise, you could actually make it worse because of the error in forecasting. So one approach is this notion of, can you move the metric over to the machine learning? The other is you can do things like run some simulations, build some simulations of the system you're really trying to optimize and simulate error, just fake predictions. Take the real data, add error plus minus to it, fit that into the simulation, and then you will be able to determine what level of accuracy do you need for your forecasting model, and then you go back to the machine learning and you address the issue that way.
I want to add an example to what Elena said. I was reading about this face recognition machine learning model in hospitals, that it looks to your face, are you going to have a stroke within the next 2 minutes or not? So you need actually a high speed model there because you don't have much time. It's actually going to repeat it maybe 3 times. So within a few seconds, the model should predict you're going to have a stroke or not. So like accuracy doesn't matter much. It's okay if the model says you're going to have a stroke and you don't have it. It's okay, Yeah.
There's different types of accuracy too, right? You got to figure out what's more important, the false positives or the false negatives. So
exactly.
Okay, I think that's moved us nicely on to I guess the second question we've more or less covered here about what is needed to help machine learning better assist in these domains. In terms of revolutions from, I guess, academia, what could we be working on that would make this more applicable? Or in terms of the broader structures and the software engineering and so on that goes behind this. Did anyone else have further thoughts to add to that in terms of how we can make faster progress? Otherwise, if we've, I think, covered a few different points there, I would like to open this up to questions from the audience. I think we've covered, I guess, so Rajiv had the question Elena referred to on the balance between speed and performance. Were there thoughts from anyone else on how that should be handled? I guess it is highly context dependent, as we've discussed. Otherwise, I would like to get the audience more involved here. So either, I guess, raise your hand or just unmute yourself, or type your question if you would prefer. Okay, I see we have a question from Graham to get us going. One self-declared computer scientist, but all the panelists are performing similar work. So could we elaborate on our journeys into the energy machine learning field and that blend of the two, I suppose, and knowledge barriers that have needed to be overcome? Great question. Who would like to start on that?
I can start. So my barrier was sort of in the opposite direction to the from the computer science to the domain. What has helped there was this fact that I started my career in consulting and I worked across domains. And so with each new domain that I had to work in, my ability to handle the next domain got better. You know, figured out what kind of questions to ask out of the domain experts, how to be taught the new field. But still, there's always, when you apply these techniques to a new domain, there's always a bit of a learning curve at the beginning. And so I've had to do that for energy. You know, like I was not familiar with the physics side, like what's the difference between power and energy again? And, you know, in the grid, what's all with all these phases, what is that? And so on and so forth. So there's definitely always a learning curve in that direction. But I'll let the other people speak about the opposite.
Sure, I can jump in here. I come from environmental science and engineering, and I got quite interested in complex systems theory as a PhD student, and that was the framework that I used. So that lends itself quite well to a problem-orientated approach as opposed to any particular analytical lens. And so I think that, you know, that's what I tell my students, you know, focus on what the problem is and then go find the tools to solve the problem rather than the other way around. And so that's the approach that I still take today. And so that, you know, you need to be comfortable with messy problems, with ill-defined problems. You need to be comfortable going from one discipline to the next, both in terms of methodology and also core domain expertise. And that lends itself very well to collaboration. So that's the upside. You know, you need to talk to people who understand, you know, have much stronger depth in these fields than you do. So those are all, I think, learning tactics. You know, some of the things that I'm, like I said, coming from natural sciences and engineering, you know, I still code in MATLAB, and I'm desperately trying to keep up with my graduate students and all of the new programming languages and things like that. So that's always an ongoing struggle. But I think speaking to a point that was raised before, I think it was by Yi, there is this tendency for students to get off the shelf software programs and pre-trained you know, networks and things like that. But then, you know, I always like to focus on, well, what are the fundamentals here? You know, you need to have a real, you know, an understanding of the fundamental maths behind it to be able to deploy it. So I tend to go back to the fundamentals of things and then, you know, look for good problems to work on.
I had a different experience from Martino. With my PhD, I wanted to see everything, you know, complicated. When I was doing my first ML project, I was like looking at, you know, batteries, like charging and discharging like profiles, or, you know, things like that. And like capturing all these details in my model, it was like too complicated that, you know, people couldn't understand my model, or even my model was not really functioning as it was supposed to work. You know, when I was doing my time at university, we were making this joke of like software engineers or software engineering students, when they can print hello world, with a language. They just put that on their resume that they know that language. I was like, no, but actually that's the trick. You should start simple. Like in my opinion, like your first ML model should be actually like very simple, just like reading from, I don't know, like a CSV and do some like very basic, work and go after that. And I think I started from just like using a spreadsheet, like train my model and, make it better. And then end up using, some like weather APIs, for example, to get real-time data and make my script, automated, just move from the Jupyter notebook, to automation and like toward having a software. And like, why do I use my laptop for this? I can shift, to the cloud, make it more reliable, and just I can integrate this with another software we have, things like this. But my opinion, you should always start like simple and build on that.
So actually, the integration of energy and machine learning is just as an example of interdisciplinary researchers. So actually, most of the graduate students or researchers are doing interdisciplinary research. For example, at the combination of energy and the wireless communication or something like that. So it's just the example, in my opinion. Actually, a general rule to learn a new area, in my opinion, maybe the first one is that we should be willing to devote our time. It's very time consuming to get familiar with a new area. For example, I'm now working on wireless communication and its application to power systems. I think it's very hard to load basic rules and so many basic knowledges about the wireless communication. The other one is that you need to interact, communicate, or talk to your friends or the students in other areas. For example, at the beginning, I talked to many of my students who are in computer science, so I can learn so many ideas from them. The other one is that you should learn by yourself, reading papers, learn some online courses, and also read books or something like that. So the first rule is that you need to devote your time, yes. And the other one is that you should be critical thinking, because you need to identify the intersection point between energy and machine learning. Why this kind of method can be applied in in any systems. So be critical, and you will find more ideas and more applications.
Go to meetups, whether virtual or in person, when they come back. The data science meetup in Vancouver brings together a really wide range of backgrounds. So I've found it really useful to see how people from other domains think. There's physicists there, there's mathematicians, there's people from various other sciences, there's economists, so exposure to other ways of thinking is good.
Great. I think that was very, very illuminating answers to Graham's question. And so now, due to pressure of time, we will move on to the student presentations. There will be what's it called, the after party session after this for another half an hour, where if you have any other questions, maybe we can have an ongoing discussion about those later on. But for now, let's move over to Graham for the first of our snapshot kind of presentations of work going on at UVic.
Sure, hi, I'm just getting my presentation set up here. Okay, so hello, my name is Graham Wilson. I'm a Master's of Applied Science student here at the University of Victoria, and I'm supervised by Dr. Curran Crawford, and I'm going to try and give a 5-minute really quick overview of some of the work I've been doing that kind of talks about these sorts of topics in relation to battery modeling. So just to start off, we're looking at the energy storage or battery and energy systems nexus. So On the left there, we can see the explosion or the expected projection of energy storage in the next 10 years, and it's immense. And a lot of it has to do with decarbonization and energy storage research, whether we're talking about enabling renewables with stationary energy storage systems, or we're talking about replacing internal combustion engine vehicles with battery-powered electric vehicles, or whether we're talking about something a little bit more complex, like easing stress on the electrical grid with distributed storage. It all kind of comes down to, or a lot of it comes down to energy storage. So on that note, it becomes really important to have efficient, adaptable, and flexible energy storage models so that we can properly model and plan out these system changes in the next 10 years. So just to talk a little bit about what we actually are modeling, the first types of models we have are state of charge models. So these are short-term models where we're looking at electrons moving back and forth inside the cell and looking at what sort of power and current we can get out of a cell. And then the second type, which is on a different time scale, is the state of health models. So long-term models where we're looking at the inside of the cell itself and how it wears out as we use it. And both of these models are very important for the planning, but I particularly am more interested in this second type of model, which is looking at the long-term performance and how that cell is going to behave after a lot of use, so we can make sure that our models accurately reflect the real world performance of the cell on day 0, as well as on day 365 or day 3000, perhaps. And so trying to model these is a bit of a challenge, because we can see in this little diagram here, it's quite small, but there's a lot of things going on here, a lot of electrochemical processes that are fairly complex to begin with. So there's a lot of different mechanisms to try and model if you're trying to look for a physics-based model. As you try and build up these physics-based models, they get increasingly complex, hard to understand, and hard to apply to different situations where speed or just complexity becomes a barrier. So this is one situation where I'm going to say data-driven models, just to avoid some of that controversy that Dr. Evins mentioned at the very start with definitions of machine learning. But whether it's truly a complex sort of machine learning situation where you're trying to predict which cell out of a batch of manufactured cells might fail early, or whether you're just trying to quantify the life of a cell under different sorts of duty cycles and operating conditions, data-driven machine learning type models are a really good alternative here. The research has shown that. But one big barrier, and we had heard this mentioned a couple times, specifically Dr. Wang had talked about open source models. So kind of in the similar vein with battery modeling, one of the big barriers is open source data. So a lot of the situations, if we're talking about grid modeling or building modeling, there might be a lot of data floating around from real world operations. But when we're trying to model the degradation and the long-term health of a cell, we need really precise long-term data under very specific conditions. So we have good diverse data, and we can be sure that our data is going to generalize. And unfortunately, the amount of data sets floating around with this sort of data, you can probably count on one hand. So that is one big challenge. But excitingly enough, IceVic has kind of moved in to fill that niche a little bit. So this isn't specifically my work, but it's some work that's been a collaboration of several different researchers in IceVic, and is just kind of finally taking off to get some real world data going. But this is our own in-house battery testing facility. So we've got on the left here, the battery testing rig and a thermotron thermal chamber. So what we can do, as you can see on the right, is throw a whole bunch of batteries in there and test them under different sorts of duty cycles and different sorts of thermal loads. And we can come up with our own high quality data set and our own models that we can then drop into all these sorts of different applications we're looking at, whether it be electric vehicles or buildings or anything other than that. So that's my presentation that I've got. It was very quick, but hopefully I gave you a good idea about some of what's going on in IceFic and in my research group to do with energy and machine learning.
Great,
Thanks.
thank you, Graham, and great comments about open data there for sure. Okay, and now our final student presentation is from Paul Westermann. You are going to share your slides, I guess, Paul? Yep.
Okay. Hello, everyone. My name is Paul. I finished my PhD studies last year, actually, and I'm now working as a postdoc for the group of Ralph, the Energy in Cities group. And today I'm going to talk about machine learning to scale building analytics. To always try something new, in this presentation, I'm trying to make a purely example-based presentation. It's mostly dealing with previous work we did together in the group. And there are basically three ways on how we scaled building analytics. First is scaling the analysis of the existing building stock. This is the first example I'm going to talk about. Then on helping or scaling building simulation with machine learning augmented physics-based simulation called surrogate models. And then the last example of, which is kind of the holy grail of merging the two. So I come to the first example is on how to analyze the building stock. And in this first task, or the first problem we looked at was, can we actually learn anything about the building heating system? Oh, jumping by itself. Building heating system, just based on smart meter data, because smart meter data is the most standardized data we get on buildings. And how did we do this? We looked at the smart meter data and compared the air temperature and the smart meter output just in the simple plot. The plot is called the energy signature. And the interesting part about these energy signatures is they tell us a lot about the different buildings. So now if we make these energy signature plots for any building in a city, we can see quite some different characteristics. And, oh, why is this just jumping? Okay, let me, I don't know why this is doing this. So, and now when we look at the energy signatures, we can actually extract the shapes of the energy signatures for each building. And now if we do that for multiple buildings, we can start to cluster the shapes of all the buildings. And this is what we did in the study and found out that the clusters we derived actually correlate really well with the heating system installed in the building and the building type and the type of the building we were looking at. So this is the first example on how we use actually in the end a very simple approach, just the energy signature, to learn about or to scale the analysis of the heating system of a building stock. Okay, then I come to the second example, and I hope now that the jumping is not automated anymore. And this example is called machine learning augmented building simulation. And if we look at a building design process, each building is pretty much unique, and it has multiple parameters architectures or building designers are looking at. So here in this example, there's a building which has 32 parameters, and all of them are considered when designing the building. And there are a lot of questions like, what if I change the window size by a little bit? How much does it affect the performance of the building? And to do that, what we would like to do is to run huge parametric analysis to basically explore the entire design space spanned by all these design parameters. And this is what we do a lot in our lab, is we try to use machine learning to explore this design space. And how do we do this? Well, we have a first idea of a building, and then we define certain design parameters. So in a simple case, for example, the window to wall ratio, WWR, or the solar heat gain coefficient. And then for these two parameters, we start to perform certain common physics-based simulations. And this, in the end, provides us with some small data sets where we have simulation inputs, here the window to wall ratio and the solar heat gain coefficient, and some performance metric like the annual energy consumption, AEC. now what we use machine learning for is to automate the process, or to learn from these first simulations we did and make a surrogate model which basically predicts what a simulation would output for a certain combination of these parameters. Well, the problem of this process is that once we want to have a lot of parameters we are looking at, we get to a curse of dimensionality. And in this regard, we came to a specific problem when we actually want to look at the impact of climate on the building performance. And here, this figure actually shows 17 time series, and each of them represents one climate variable. For example, the top black line shows the outdoor temperature. And now if we want to train a surrogate model which is capable to process these 17 time series, this becomes a problem. And how we solved this, in the end, we trained a convolutional neural network with these convolutional kernels processing the time series data to get a surrogate model which is capable of predicting the impact of climate on the building consumption. Here's the heating demand. This is on the very right. I don't want to go in detail about the architecture of that network. It's just that we use the convolutional network to process time series data, climate time series data. Then we trained this network on simulation taken from very specific defined data sets of climate simulations, which were based on the Köppen climate definitions. So here you see the different Köppen climate zones encoded in the different colors. And for each of the climate zones, we took 5 climates and ran simulations for these climates. And now the exciting part about it was, although the input dimensions got really, really big, the surrogate model was still capable of processing it and producing high accuracy heating demand estimates. And for example, what does it mean for the application? Here you see, for example, a map of the heating demand for one specific building design for Canada. And the exciting part about that figure is that our surrogate model can produce the heating demand estimates in a fraction of a second for Canada in total. So we go basically from one building to from one location to entire countries we can analyze now. And then we come to the third example, is how can we bridge the two? So, and this motivation is based on problems, or this idea is based on problems. So first is that standardized high quality data on existing buildings is scarce. So for example, in the first study I showed is that where we try to classify the heating system of buildings, we only had a data set of around, what was it? I think 1,000 buildings. And the problem with that is we cannot really train any high parametric machine learning model with it. And that's why we also went in the other way and did this energy signature analysis. So if we really want to train some deep machine learning models, we need more data. And now the question is, can we learn within the simulation environment, the physics-based simulation environment, to train our machine learning models, and after that apply them to the real world? I mean, this is a dream, but we are kind of working on it, and I think future research will probably, is super promising in this realm between simulation and machine learning. And how we did this, it's self-explanatory. After I gave this introduction, we developed some synthetic simulation data sets using our building simulator, and very certain common parameters of building, like the material thickness of the envelope, the material type, internal loads and occupancy, some weather data and infiltration rate, because it's very it has high sensitivity on the performance of the building or the energy consumption of the building. So we varied these and generated our own labeled data set. And now what we did afterwards, we looked at different methods existing in the world of building analytics to classify or to predict the performance of these buildings. Here in that case, the heat loss coefficient. So we looked at these 7 different models, and so far we only compared these models and within the simulation or the synthetic space and classified which or found which methods are the most promising. And now we are on the brink of moving towards the real world space. Yeah, these were 3 examples of 3 papers we did in our group. The entire group was part of it. Thank you very much. And yeah, it's also my last day here at the University of Victoria. So yeah, great end here with the EnVision conference.
Great. Thank you very much, Paul. Great overview of some very varied work there. So I guess now I will just wrap up very quickly because we're so nearly out of time, but we've covered lots of great ground today from how companies want to go beyond Excel to more detailed models, the sort of forecasting approaches being applied with LSTMs and so forth, the need for both transparent models and also some form of privacy preserving models if these are to be used and implemented in policy, the broader sources of data that are available from smart devices now being deployed, other sorts of things like satellite imagery and ways that we need to do data fusion to bring those together, issues of performance drift in models and that just pre-training a model and sending it out in the world is not enough, and then the associated sort of tool sets that are needed for that, the issues of data availability and code availability to share all of our insights, and then this idea of combining off-the-shelf machine learning models with existing simulators, the whole area of synthetic data. As always, the need for data cleaning was mentioned, the idea that this can form as a bridge between different fields and different areas. So hopefully this has given everybody some great kind of insight into future areas of development and driven some excitement into machine learning and its applicability to energy. And I'd like to end firstly by thanking our panelists and our student presenters very much for their time being with us today and sharing their insights. I wonder if our panelists would like to finish with a call to action. What would you say to people in one sentence to what should they take away from today, or what should they apply in future? So perhaps we'll just go around very quickly. Let's start with Elena.
All right, one sentence. I will say gather lots of tools for your tool set so that you can mix and match and match to the problems that you'll be faced with if you go out in industry.
Brilliant. Yi?
My sentence is that try to integrate your deep understanding of the power systems into the machine learning models.
Great. Sahand?
Learn cloud computing.
Easy. Okay, and Martina?
Yeah, I would say these models are powerful indeed, and they're being driven by data, but there are fundamental questions around algorithm bias, which is underpinned by the data itself. So this is something that I think needs to be much more mainstreamed right at the undergraduate level for all of the types of technical students that are building up these models. It's something that I teach in a senior undergraduate class, but I think we need to be vigilant about these issues.
Absolutely. Okay, so I will end with our sort of virtual round of applause for our panelists and presenters. Thank you all very much. So we will have the after hours continued discussion, but I think perhaps Andrew, did you want to say something to wrap up the formal proceedings?
I would love to. I will just be very quick. And I will share my screen for everybody. Okay, I will be fast. Thanks so much, Ralph and panelists. That was another great panel. So this does conclude EnVision 2021. And a year ago this time, I had no idea what we'd be doing for EnVision. It was on my mind the minute we went into pandemic lockdown. So for those of you, this is your first EnVision. Typically every 2 years, we try to have a couple of days of what we've just done online, but in person. And it's always been great, usually a good chance to connect with alumni, but also bring in some great speakers like yourselves and build some new connections. We usually have a fantastic dinner after the first night, which is a lot of fun down at the U Club. So that's the unfortunate casualty of this year, but I guess as Curran said earlier in the week, our carbon footprint is a lot lower, which is part of the theme here. So yeah, it's definitely different, but I think it was successful. For those of you who didn't make the other sessions this week, you can go back and view these when you have time. Check out our YouTube channel. All of them are posted so far, except for, of course, yourselves, but that will be up shortly. So we had one of the things I really enjoy about EnVision, I think for most of us who are academics, we tend to go to our very specialized venues, right, where we tend to be in a bit of an echo chamber talking to everybody else who's working in the same field. So one of the things that I really love about this meeting is the breadth, and I'm always learning new stuff. Same thing this year, really wide range of topics, all very interesting, but it constantly reminds me of why I guess I got into academics, like many of the rest of you. I just like to learn stuff, and I'm a bit of a crow, I guess, which might be a crow in terms of I'm attracted to shiny new objects, and which maybe isn't a good thing for an academic because you want to stay focused too. But I love learning new stuff, and so this has been a great week. And again, your panel, I learned a bunch of new things, so thank you very much. And just before I hand off for your social time, I wanted to thank all the panel moderators, Curran Crawford on Tuesday, Kevin Palmer Wilson Wednesday, Madeline McPherson Thursday, and Ralph Evins today. And also there were some helpers and organizers behind the scene, Pauline Shepard, Jeremy Rashidi, Theo Christiaanse, Jake Monroe, who's done all the tech support or most of it, and Rad Hagi. So I thank you to all of you for making this work. And I think I didn't see any major glitches. Maybe some of you did, but I was impressed. I guess that's a testament to our comfort level with Zoom now. So yes, thanks so much, and enjoy yourselves for the last bit. And hopefully, who knows what we'll be doing in 2023, but hopefully we'll see everybody either virtually or perhaps in person. So thanks so much, and back to you, Ralph.
Great, thanks, Andrew. And I would like to extend the invitation to any of our panelists today who find yourselves in Victoria in the after times that are hopefully coming soon. We would love to host you at UVic for the meal that Andrew promised. That's unfortunately been postponed this year. But otherwise, I guess that's it for our formal proceedings. So if anyone has any other questions that they'd like to jump in with, or general items, not just for the panel, just generally, who would like, anyone who has any further comments. Otherwise, yes, I'd also like to thank Jake for your technical support and Theo today. This, I think, went very, very smoothly. Otherwise, if our panelists do have to drop off, I'm aware you are very busy and you've given us lots of your time already. Great final point there, Martino, about bias in these algorithms. I was reminded of this in one of Paul's slides there, where he showed all of the climate zones that we plotted these models for. I guess this is a different form of bias, but we initially used a set of weather files that we found online, common repositories for these that we use in building simulation. And we ran our simulations with those, and it turns out that's actually building some bias into the process, because only rich countries put their weather files online. So it's really good at designing HVAC systems for North America, and slightly less so for Europe, and then fades out rapidly, and there's basically nothing in Africa. And we thought, okay, no, this isn't the right way to do it. Let's go the other way and say, let's try and get the broad spread so we could simulate for anywhere on the planet. That was our goal with this kind of ultimate surrogate. So we sampled those climate zones Paul mentioned, so that we've got an equal number in each climate zone, which has maybe gone too far the other way, because we now have 3 in Antarctica, which might be overkill slightly, somewhere where there really isn't going to be anything built. But yeah, we bumped into that from an interesting perspective. That do you try and be theoretically as useful as possible, which is basically where people are going to use these models to build buildings, and they have to be fairly, I would say, expensive advanced buildings to be maybe contemplating using our software there? Or do you say we should be as inclusive as possible and say, actually, this tool should be equally applicable to somewhere in Africa as North America, for example?
Yeah, it's interesting. It's a great point. We didn't touch on it, but certainly I think a strong argument for the use of mixed methods and conventional physics-based models alongside machine learning is really just the scarcity of data, depending on where you are. So you bring up a really great point in terms of trying to conduct some of this analysis in other countries, and myself in cities where data is scarce. So you immediately have a data bias there, setting aside the particularities of the data bias when you dig down. Even here, as I mentioned, some of the work that we're doing is really trying to understand different demand profiles, and there's just a lack of data on certain segments of the population here. So that's a problem that we need to be aware of.
Curran has a great question in the chat about how this should fit into our undergraduate curriculum. Curran, do you want to say your question? Spark the discussion.
Sure. Yeah, we have this very crowded undergraduate curricula that we keep adding things to. So I'm just wondering thoughts from people around where might this either have to stand alone, where would you integrate it into courses in your range of different areas? Interested there.
I know that's a good question, Curran, and especially given the amount of required courses, particularly for engineering undergraduates. That's always a challenge, right? So they get to take maybe the one course about on something else. So that might speak to more systemic challenges of kind of broadening out the undergraduate curriculum or reducing the amount of required course load. But I know, computer science, and Elena might be able to speak to this better, but I certainly know at UBC, computer science and computer engineering, they discuss issues of algorithm bias, in certain courses that are focused on broader societal contexts of technology deployment. I know at UBC there is an elective course on technology and policy, something like this. So I think that might be a venue to really expose students to data, both the broader applications, but also some of the challenges with the use of data.
Yeah, I'm not sure I can answer how do you find room to fit it, but I do think it'd be good for the coming generations to be exposed to notions of of data-driven decision making. Maybe let's call it just even the basics of analyzing data and the ethics side of issues that come with analyzing data. I think the sooner we can, and these don't have to be like really deep, teach them, the mathematics of a machine learning model. I think it's about teaching the concepts and also what can and cannot be done. So Martine mentioned at the very beginning that a bit of humility is good in terms of what can we predict and what not, because one thing sometimes people going from academia to the business world find is that there's this perception that if I have data, I can do anything. And obviously it's not like that. You have to have the right amount, the right kind of data, the right amount of data, and so on for the question that you're answering. So yeah, all in favor of trickling things earlier on, but I can't speak to the bandwidth, unfortunately.
As you know, I have opinions on this, Karen. I think we could cut a bunch of those calculus courses and fill in some stats. That might be a good start. No one needs 5 courses of calc and then 0 knowledge of statistics, even before we get to machine learning. And then if we were to, so part of it is the underlying skills in data driven, but also the software side of it. So getting Python earlier in the curriculum, getting little coding exercises scattered through every course, not just waiting until the end after they've gone down the Excel path and got stuck, could make some difference. It's, I guess, a question at the undergrad is more complicated. At the master's level, particularly the taught masters that are more common in Europe, UCL has a master's in energy data analytics. So a whole, I guess it's a 1-year program, but a detailed taught program on exactly what we've spoken about today. So I'd be keen to see something like that possible here. Do any students on the call have any opinions about how we could be better putting this into places where you would like to learn it? Or any others? Maybe we've run out of students at this point.
I definitely agree that it should come as early as possible, because I think it's easy to have one class about something like this and then you forget about it all. But I think it's when you see these skills come up year after year, whether it's, you know, even something like MATLAB is a similar experience. Like you can take it in one class and you forget about it. But if you have, you know, just a touch of Python learning year after year, I think that's where you're going to get the benefit.
Integrated curriculum, whole other challenge. But,
yeah. Well, I think, like you said, we have lots of calculus class. We have a stats class, but it's very classical stats that doesn't set you up at all. Even the uncertainty quantification stuff I've gotten into, I had no idea about that. It's just not even talked about at an undergrad level. So maybe it is like Martino and Elena saying, it's the concept, at least, so people have some awareness of this space. And great, thanks.
I'd be interested how they're handling this in, I guess, UVic, we have computer science and also software engineering, but I hire lots of them as co-op students, and they're very useful, but they have very differing levels of, there's certainly no core courses I'm aware of that enforce the sorts of machine learning stuff we've talked about today. Whereas I guess I would have thought that could be considered core these days, but maybe their curricula change as slowly as ours do.
Yeah.
Elena had a great point about how to find other sources of learning. I think something we come back with too often when we're trying to cram everything into our undergrad curricula is actually, if I'm hiring someone as a master's student, or I'm sure out in industry the same, they've learned 10% of what they need in an undergrad degree, and they've learned a lot of other soft skills like how to learn things quickly, and then they have to go and find it. They have to find whatever it is, YouTube, or I was going to say textbooks, but that sounds really old-fashioned, but ways of picking this stuff up that don't involve taking a course.
Yeah, different people learn different ways, so I wouldn't discount books. I know people that like to learn by reading books. Yeah, and the point that I'll make there, maybe just to add, is you can't stop learning after you've finished your degree. So whether you do it by books or by reading papers or by taking further online courses, which are now you can take for, you know, there's like all these MOOC platforms, Coursera and Udemy and Udacity and so on and so forth, edX, etc. Yeah, I myself continue to do that, you know, 15 years out of school. So you can't really stop learning. But yeah, I would, I guess, advise going a bit for breadth as well, not just depth.
Yep, I will look up that book that you put in the chat. That looks great. And in terms of other relevant resources to this, there's I think it started as a newsletter, but really a platform called Climate Change AI, which is I find a great source of this kind of hybrid. A lot of it is, I find it, this is my personal bias, I find it not engineering centric enough. It's basically data scientists who want to save the planet. But a huge amount of that right now is sort of predicting storms with rainfall data or something. Kind of, I find it very much on the sort of looking at the data end of it rather than necessarily the solutions and delivering end. But it's definitely a very worthwhile endeavor, backed by some of the huge names in AI. From that sort of, I think it grew out of a workshop at the NeurIPS conference. So very, very much whatever. I think Yoshua Bengio and sort of the big people who are saying we should use ML for good are behind that. So I recommend that.
Yeah, I will actually say that. So I haven't gone to the latest NeurIPS, but I went to it two times ago in person. I was in Vancouver in person. And I was a little bit disappointed with the amount of energy-related, clean tech-related applications discussed at that conference. Whatever it was sort of climate stuff, and it was more like predicting the bads that could happen and less about the solution side of things. So, yeah, I'm hoping that will change.
Yeah. No, I certainly see that. There's this idea that, what's the phrase, that if you can't measure something, you can't change it or something. This idea that we should be analyzing the data and seeing if we can really understand the problem. And I come at it from a completely opposite angle, that, well, we know what the problem is. We need to reduce our emissions by 90%. Now let's actually invent things that are going to do that. But yeah. Okay, I think Martina had to drop off, and I'm sure other people
yes, it seems to have quieted down. So if people don't mind, I think I will jump off as well.
Thank you for your
but
time,
thank you
Elena.
very much for the invitation, and I've loved hearing everybody else's thoughts on the topic, and looking forward to watching the videos from the other sessions as well. So thank you to all the organizers for making this happen, and the other panelists as well.
Great. Thanks, everybody. Pauline, did you want to say any final words from an IceFix side? Has it been a good substitute for EnVision in person?
Hi. Yeah, no, I think can everyone hear me?
Yep.
Just want to say thank you. I found it absolutely fascinating. And as I'm kind of a vaguely educated amateur, everything, I mean, I've enjoyed it more than any other EnVision because I've been able to concentrate on it, but it's been great. And the breadth and the innovation on some of the presentations was incredibly engaging. And I've actually written, I haven't written so many notes since I was at university. So thank you very much. It was great.
Great. No, it's
be nice to have a glass of wine to say hi to.
Absolutely.
We will do that at some point. But
I hope we can all do that soon. Exactly. And nice to see you all again, even if only virtually. Hopefully we can do this on campus soon.
Take care and have a safe next few months.
Yeah. Okay. Bye, everybody.